In the year 2004, an epochal moment in cosmic discovery unfolded. Astronomers, meticulously sifting through the torrent of data transmitted by the Wilkinson Microwave Anisotropy Probe, or WMAP for short, stumbled upon an anomaly that defied easy explanation. This probe, designed to capture the ancient whispers of the universe, the faint echoes of its earliest moments in the form of the cosmic microwave background radiation, had unveiled something truly peculiar. Across an unimaginably vast expanse within the constellation Eridanus, an immense region of space exhibited a temperature profoundly, inexplicably lower than the average temperature of the cosmos. This phenomenon, stark in its deviation from expectation, was christened the Eridanus supervoid. The sheer scale of this supervoid is almost impossible for the human mind to grasp. To provide a sense of its staggering dimensions, consider this. One could hypothetically align approximately 20,000 galaxies, each comparable in size to our very own Milky Way, in a straight line from one edge of this colossal void to the other. To further underscore this scale, let us recall that light itself, the fastest traveler known, requires a staggering 100,000 years to traverse the expanse from one side of our Milky Way galaxy to the other. Imagine, then, the journey across the Eridanus supervoid. Its implications were immediate and profound, sending ripples through the established frameworks of cosmological understanding. Among the numerous explanations that arose in an attempt to account for its existence, one particular hypothesis resonated with an almost poetic grandeur. The idea that this cosmic anomaly might, in fact, be an imprint, a residual echo of another universe. A universe that perhaps diverged from our own during the primordial genesis of all things. It suggests a fracturing, a splitting of realities, leaving behind a subtle yet monumental scar on the fabric of our shared existence. This concept, born from the depths of mathematical modeling and theoretical physics, posits that what we perceive as an inexplicable void could be a relic of a fundamental cosmic divorce, an interdimensional signature etched into our early universe. 4 years later, in 2008, another profound discovery emerged, casting further shadows of doubt upon our prevailing cosmological models. A dedicated team of astronomers, under the astute leadership of Dr. Alexander Kashlinsky, presented compelling evidence of a vast coordinated movement of at least 400 galaxy clusters. These colossal collections of galaxies, each comprising hundreds or even thousands of individual stellar islands, appeared to be streaming in a unified direction towards an enigmatic region located somewhere beyond the boundaries of our currently observable universe. This discovery, quite frankly, was astounding. According to the standard cosmological model, the motion of galaxy clusters throughout the cosmos should largely be random, driven by localized gravitational interactions and the overall expansion of space. Yet, here was clear evidence of a grand overarching current, an unseen river of galaxies. This perplexing phenomenon was appropriately dubbed the dark flow, drawing an analogy to the equally mysterious dark matter and dark energy, not because it possesses any inherent visual darkness, but rather because its fundamental nature and ultimate cause remain utterly unknown to science. The very name acknowledges our profound lack of comprehension. The findings were so unexpected, so deeply unsettling to established theories, that Dr. Kashlinsky, commenting on this potential paradigm shift, articulated the sentiment with remarkable candor. He stated at that moment that the available information was insufficient to fully grasp the nature of this force or to definitively characterize it. His team could only assert with certainty that, somewhere incredibly distant, the universe as it truly exists differs profoundly from the localized patch we directly apprehend. Whether this implies the presence of an entirely different universe, a distinct manifold of space-time, or some other unforeseen cosmic architecture, remained an open and tantalizing question. The feeling of being on the precipice of an entirely new understanding was palpable, a thrilling yet humbling realization of the limits of our current knowledge. Fast forward to our present era, the year 2023. A groundbreaking article, recently published in the esteemed journal Nature, presented yet another series of observations that further challenged our cosmic understanding. Utilizing the unprecedented capabilities of the new highly advanced orbital observatory, the James Webb Space Telescope, astronomers detected a total of 6 celestial objects that, by all accounts of current cosmological theory, simply should not exist. Let's consider the cosmic timeline for a moment. The Big Bang, the singular event marking the origin of our universe, occurred approximately 13.8 billion years ago. These newly discovered objects, however, appear to have formed a mere 600 million years after that primordial explosion. This places their genesis in an exceedingly early period of our universe's infancy, a time when conditions were thought to be far too nascent for such substantial structures to coalesce. We are speaking of 6 enormous galaxies, colossal assemblages of stars and gas, whose very existence in such a young universe confounds our most sophisticated models. According to prevailing theories, galaxies forming at that early epoch should be, at a minimum, 10 times smaller than these behemoths, and by more conservative estimates, possibly even 50 times less massive. The calculations derived from our current cosmological framework suggest that there simply shouldn't have been enough ordinary matter, the stuff that constitutes stars, planets, and indeed our very bodies, to facilitate the rapid formation of such immense stellar cities. One of the lead authors of this pivotal research, Dr. Erica Nelson, starkly encapsulated the gravity of the situation. She declared that if even one of these galaxies proves to be genuinely real and confirmed, it would fundamentally dismantle our current understanding of cosmology. The implications are that severe. While no definitive explanations for this startling phenomenon have yet emerged, the scientific community is already engaging in spirited discussions and even lighthearted conjecture. Among the more whimsical suggestions is the notion that perhaps we need to introduce a concept of dark time, an unknown influence that somehow accelerates the development of cosmic structures far beyond what our present theories permit. Such playful speculation, while not rigorous science, underscores the profound bewilderment and the urgent need for new paradigms to make sense of these unexpected revelations. Have you noticed a recurring theme, a consistent refrain woven through each of these remarkable discoveries? In every instance, the same disquieting yet ultimately exhilarating phrase echoes. This discovery has called into question the fundamental postulates of our cosmological model. It is a testament to the dynamic, self-correcting nature of scientific inquiry, but also a stark reminder of the provisional nature of our knowledge. If all these foregoing observations are eventually confirmed, if the anomalies are not merely due to the inherent imperfections of our observational methods, if the brilliant minds behind these findings have made no errors in their intricate calculations and interpretations, then we are unequivocally facing a crisis in our established theories about the cosmos. And here's the crucial point. This is profoundly good news. Crises in the scientific realm are not harbingers of collapse, but rather the essential precursors to revolutionary breakthroughs. They signal the limits of existing paradigms, compelling us to forge new conceptual tools, to reevaluate our fundamental assumptions, and to expand the very boundaries of human understanding. It is through these moments of intellectual disequilibrium that science truly advances, Yet, despite such profound anomalies, such cascades of cosmic conundrums that routinely punctuate the annals of scientific discovery, cosmologists, with an almost unwavering resolve, continue to inscribe the word universe with a capital U in their treatises and discussions about the totality of existence. And the emphasis here is not merely on grammatical convention. There is a deeper, more philosophical implication embedded in that capitalization. A subtle presumption that we, as a species, have grasped the ultimate nature of all things, even as the universe itself continually presents us with riddles that defy our most sophisticated frameworks. You see, a short while ago, in the quiet solitude of a late night, as is often the case when profound questions tend to surface, I was gripped by an overwhelming desire to comprehend what, theoretically, might lie beyond the very boundaries of the universe. I found myself pondering the most fundamental of inquiries. Does such a boundary even exist? Is there a literal edge that we could, in principle, approach, perhaps even peer beyond? What would transpire if one were to simply embark on an endless journey, continually moving in a single, unwavering direction towards any arbitrary point in the celestial sphere? Would this ceaseless motion ever reach a termination point? And if it did, what form would this ultimate frontier assume? Would we perhaps collide with an impenetrable obsidian wall? Or would we somehow pass through it? And if so, what realm, what unimaginable expanse would greet us on the other side? For those who might dismiss such inquiries as naive or unsophisticated, I urge a moment of reconsideration. The question of what lies beyond the cosmos has captivated and tormented humanity's most astute minds for millennia. A substantial portion of historical cosmology, across diverse cultures and epochs, was inextricably linked to notions of a discernible center and an ultimate edge of the universe. Consider, for instance, a fascinating 19th century engraving, a visual artifact that powerfully encapsulates how people in the medieval period might have conceptualized the very boundary of the universe. This intricate image, filled with symbolic meaning, reputedly depicts a traveler pushing through the celestial dome, breaking past the perceived firmament to glimpse a hidden, intricate mechanism. A grand, clockwork contraption, perhaps, that governs the entirety of creation, lying just beyond the veil of our perceived reality. It is a potent reminder that the human quest to define and locate the cosmic edge is as ancient as our capacity for wonder itself. Driven by this nocturnal quest, I plunged into the vast ocean of online information, seeking the insights of contemporary thinkers. What did the wise people say on this profound subject? To my initial dismay, I discovered a striking homogeneity. Almost every article, every video exposition on this topic, seemed to adhere to a depressingly similar template. This common structure was perfectly, almost ironically, articulated by a trenchant comment I encountered on a forum beneath yet another article titled, "What Does the Edge of the Universe Look Like?" The comment succinctly summarized the prevailing narrative. First, talk about the Big Bang, then talk about it again, and again. Finally, subtly substitute the phrase edge of the universe with edge of the observable universe, prophet. And indeed, this pithy observation captured the very essence of my frustration. It is, of course, a well-worn truth, almost a cliché, that if we were to employ immensely powerful telescopes and direct them towards the farthest reaches of space, we would not be perceiving a literal, spatial edge of the universe. Instead, what we would apprehend is its temporal beginning, its earliest epochs. This is the often repeated, yet still profoundly mind-bending reality of light travel time. When you are engaged in conversation with someone seated at a nearby table, You are actually perceiving them not as they are in this very instant, but as they were a minuscule 3 nanoseconds in the past. When our gaze falls upon a distant star, such as the brilliant Betelgeuse, we are beholding it as it existed approximately half a millennium ago. For all we know, that colossal star might have already concluded its life cycle in a spectacular supernova explosion, its light still traveling towards us, bearing a message from the past. Even the Andromeda Galaxy, the largest member of our local cluster, and currently hurtling towards our Milky Way at an astonishing speed of around 400,000 kilometers per hour, is, for the same reason of light delay, actually a full 900 light-years closer to us than its current light image suggests. And 900 light-years, let me assure you, is an immense distance. For context, the closest star to our Sun, Proxima Centauri, is a mere 4.24 light-years away. Yet, even with our most advanced modern technologies, a journey to that star would require tens of thousands of years. The fundamental takeaway is clear. We cannot simply gaze upon a distant celestial object and perceive it in real time. The farthest point we are capable of observing is, in essence, the location from which light has had just enough time to reach us since the epoch of the Big Bang. This conceptual perimeter defines the quote-quote boundary of the observable universe, and it is precisely this boundary that held no interest for me in my current quest. Why? Because it is almost a certainty that beyond this visible horizon, the cosmos continues its boundless, enigmatic sprawl. I was not seeking a mere perceptual limit, but a genuine, underlying physical boundary, or at least a compelling theoretical construct, however exotic, that could serve as intellectual sustenance for this profound meditation. And eventually, after a protracted and circuitous exploration, I did indeed find something to ponder. It was a long journey, marked by numerous intellectual detours and conceptual hurdles, the main stages of which I will now endeavor to recount for you. Crucially, my persistent search ultimately led me to the profound insights contained within a particular book, Cosmology, the Science of the Universe, by Edward Robert Harrison. From the meticulously crafted arguments within its pages, a startling realization began to crystallize. It is entirely possible that my very question about the edge of the universe might be fundamentally misconceived, or at the very least, based on a narrow, insufficient understanding of what the universe truly entails. Even if such a boundary were to genuinely exist, and even if we were to arrive at an understanding of it by the conclusion of this expansive contemplation, the nature of that understanding might be far more subtle and profound than a simple spatial frontier. The book itself is a venerable work, and its author, Edward Harrison, has long since passed from this earthly realm. Yet, his legacy endures through his profound contributions. He was a distinguished professor emeritus of physics and astronomy at the University of Massachusetts, a scholar whose achievements and accolades are too numerous to fully enumerate here. Harrison was an exceptionally well-read individual, clearly captivated by the grand sweep of intellectual history and the evolution of ideas. Throughout his writings, he consistently interwove references to poetry, classical history, and philosophy, masterfully employing them to illuminate the often abstract tenets of physics and cosmology for the uninitiated reader. What truly impressed me most about Harrison's approach was his unhesitating willingness to delve into the most profound, indeed, the most bottomless, philosophical questions that arise from our understanding of the cosmos. At the conclusion of each chapter, he would engage in a shared reflection with the reader, posing thought-provoking questions that transcended mere factual recall. This was not akin to the perfunctory check-your-knowledge sections found in a typical school textbook. Rather, it felt much more like an intimate, uninhibited conversation with a trusted friend, perhaps late at night, in the comfortable confines of a living room, where the fear of appearing ridiculous or unscientific completely dissipates. For instance, he would present an idea and then gently inquire. Many people, such as materialists and reductionists, overwhelmed by the sheer grandeur of the physical universe, believe that whatever is not contained within it simply does not exist. What are your thoughts on this? And there you sit, a modern-day cosmologist in your armchair, reflecting on the startling audacity of such a question being posed in what might otherwise be considered a formal academic discourse. It challenges the very boundaries of conventional scientific inquiry, inviting a profound introspection that is rarely found in the more rigid structures of academic writing. To my profound regret, this seminal work has not been translated into my native language, but it is readily available in English, often found in the public domain. Returning now to that illustrative 19th century engraving, which I have previously invited you to contemplate, we might, from the vantage point of humanity's accumulated knowledge, indulge in a sense of smug superiority regarding the naivete of past beliefs. We might muse on how far we have supposedly advanced in our understanding of the universe. However, as Harrison's insights gradually reveal, it is highly probable that, in terms of fundamental conceptualization, we may never truly distance ourselves significantly from the perspective of those individuals from the medieval era. The more deeply we probe, the more acutely we may realize that our models, however sophisticated, still grapple with the same fundamental enigmas, albeit dressed in new scientific garments. This realization will, I trust, become increasingly evident as we continue our journey tonight. So, where did this quest of mine truly begin? Initially, I decided to confront the problem head-on, adopting a direct and rather literal approach. I posed a thought experiment to myself. What would happen if one were to simply assemble a vast contingent of individuals, settle them aboard an immense starship, and dispatch it in a single, unyielding direction, with the explicit mission of reaching the ultimate edge of the universe? And further, what if this vessel were designed to accelerate at the maximum possible rate, pushing the very boundaries of what is conceivable in terms of propulsion and speed? A truly expansive and utterly captivating response to this very question was offered by the esteemed astronomer David Kipping of Columbia University, in a half-hour video presentation on a well-known channel. It's a highly recommended resource if you have an ear for such things. Let us then, for the sake of our mental expedition, imagine this starship. It possesses the extraordinary capability to accelerate indefinitely at a constant rate of 10 meters per second. Beyond the sheer thrill of continuous acceleration, this constant thrust would confer an additional, practical benefit upon its passengers. They would experience a sensation akin to normal Earth gravity, as the floor of the ship would consistently press against them, much as our planet constantly presses against us. You might recall that the acceleration due to gravity on Earth is approximately 9.8 meters per second squared. So our hypothetical ship's acceleration is conveniently close to this familiar sensation. To visualize the accumulating speed, in the very first second of its journey, the ship would attain a speed of 10 meters per second. In the second, 20 meters per second. In the third, 30 meters per second. And so forth. After just 1 hour, the ship would be moving at an astonishing 280 meters per second. And the acceleration would continue unabated. For the purpose of this thought experiment, we shall politely set aside certain practical inconveniences. We will not dwell on the improbable logistics of fueling such a vessel for an infinite journey, nor will we concern ourselves with the insurmountable engineering challenges posed by collisions, even with microscopic dust particles, at such mind-boggling velocities. These are mere trifles when weighed against the grandeur of our cosmic quest. After a mere 2.5 hours of relentless acceleration, our starship would have already hurtled past the moon. In just 1 week, it would sweep past the majestic rings of Saturn. And a mere 11 days into its journey, it would leave Neptune, the most distant known planet in our solar system, far behind in its wake. Yet, it would be a full 15 months of continuous travel before the ship would traverse its first light year. And it is at this juncture, as its speed relentlessly increases, that the truly bizarre phenomena predicted by Albert Einstein's special theory of relativity would begin to exert their profound and increasingly noticeable influence. To begin, the laws of physics do not forbid a ship from accelerating indefinitely. However, simultaneously, a massive object such as our starship is fundamentally incapable of actually reaching the speed of light. One can approach this cosmic speed limit with an ever-increasing closeness, to an almost unimaginable degree, but the absolute barrier remains inviolable. Consider, for instance, the protons accelerated in the Large Hadron Collider. These particles are propelled to a speed of 299, 792, 455 meters per second. One might casually observe that this is just a paltry 3 meters per second shy of the speed of light. 3 meters per second, for context, is roughly the speed of a brisk jog. Yet, despite this seemingly minuscule difference, the laws of physics dictate that it is an unbridgeable chasm. Even if one were to expend all the energy contained within the entire universe in an attempt to imbue that proton with those last elusive 3 meters per second, it would merely draw infinitesimally closer to the speed of light, achieving a proximity expressed by an endless string of nines after the decimal point, but never, ever quite reaching it. So were it not for this fundamental speed limit, our hypothetical starship, accelerating at 10 meters per second squared, would have surpassed the speed of light in a mere 45 days. However, the reality, as dictated by the elegant yet counterintuitive principles of special relativity, is far more complex. What actually transpires is this: special relativity informs us that the faster an object moves through space, the more slowly it effectively moves through time. In our scenario, this leads to a series of consequences that are anything but intuitive. From the perspective of an external, stationary observer, it would appear as though the ship's acceleration gradually diminished, its rate of speed increase slackening. Furthermore, the lives of the individuals aboard the vessel would seem to unfold in an ever-slowing, almost cinematic slow motion. Yet from the internal perspective of the crew members aboard the starship, time would continue to flow at its normal, accustomed rate, and their sustained acceleration of 10 meters per second squared would remain absolutely constant and imperceptible to them. Adding another layer of perceptual complexity, the crew members would observe that, relative to their accelerated frame of reference, time in the external universe, the realm they left behind, had seemingly accelerated. To reiterate, if the fundamental constraints of special relativity were somehow suspended, our ship would have achieved light speed in just 45 days. Yet, in the actual scenario, after 15 months of continuous flight, it would be traveling at only 87% of the speed of light. The temporal dilation, the slowing of time, as an object approaches the cosmic speed limit, does not occur in a uniform linear fashion. Instead, it follows a highly non-linear curve. For instance, even having accelerated to half the speed of light, the effect of time dilation would be almost imperceptible to the occupants. Even at a blistering 90% of the speed of light, time for the travelers would have dilated by a factor of only approximately 2. The true, Mind-bending extremes of this phenomenon only manifest when one approaches the speed of light almost infinitesimally close. Consider, as a striking example, a truly remarkable event that occurred on October 15, 1991. On that date, a single cosmic ray particle of an unknown origin impacted Earth's atmosphere. Its energy was so utterly immense that scientists, in a moment of profound awe and bewilderment, christened it the "Oh my God" particle. To put its energy into perspective, consider this. The energy contained within that single particle was comparable to the kinetic energy of a baseball traveling at a speed of 93.6 kilometers per hour. This particle was moving at an astonishing 1% of the speed of light. But the most truly staggering implication is this. For that particle, time itself was dilated. Brace yourself by a factor of 300 billion when compared to the flow of time for a stationary observer like us. This means that, for us, observing its journey from our relatively stationary position, it would have taken approximately 2.5 million years for that particle to traverse the distance from the Andromeda Galaxy to Earth. Yet, for the particle itself, subjectively, less than 5 minutes would have elapsed during that same journey. This leads to an almost paradoxical conclusion for light itself, which travels at the speed of light. For a photon, time, in essence, entirely ceases to flow. It's not that we could say, for a photon this much time passes, because there are no clocks that can travel at the speed of light, rendering such a statement meaningless. Yet I trust the fundamental principle of this profound temporal distortion has been grasped. Now let us consider the far-reaching implications of this temporal dilation. It means that interstellar travel, at speeds approaching that of light, represents a kind of Faustian bargain. If our hypothetical starship were to simply embark on a round trip to the Andromeda Galaxy and return to Earth, abstracting away the complex maneuvers of deceleration and reacceleration, a journey that would subjectively consume 56 years for the travelers would correspond to an astonishing 5 million years passing on Earth. Ponder the fate of human civilization over such an immense span of time. It is entirely plausible that the returning voyagers might find themselves in a situation where they would personally be required to reinitiate the very survival and continuation of their species from its foundational elements. Would you, dear listener, consent to glimpse another galaxy at such an incalculable cost? The ethical and existential quandaries are as vast as the distances themselves. Furthermore, if our starship were not intended to return, but rather to continue its relentless journey outward, there would come a point of no return. Upon traversing the threshold of 8.3 billion light-years from Earth, the pathway back would be irrevocably sealed. This is an astonishing concept, for there is no tangible physical barrier at that precise distance, no cosmic fence or celestial wall. Yet, once that 8.3 billion light-year mark is surpassed, the causal connection with our solar system would be severed due to the relentless expansion of space itself. No matter how intensely the ship continued to accelerate, it would never again be able to return to the vicinity of our home system. The expansion of the universe would simply outpace its capacity for retrograde motion, pushing the destination further away faster than the ship could ever hope to bridge the gap. Nevertheless, we are not here to contemplate a return journey. Our purpose is to confront the original, perhaps naive question: is it truly possible, with infinite acceleration, to reach the ultimate boundary of the universe? Let us fast forward through the ship's perpetual voyage. When the onboard clocks of our starship registered 200 years of continuous flight, an almost incomprehensible span of 10 to the power of 41 years would have elapsed in the rest of the universe. This number, for perspective, is A1 followed by 41 zeros. At this unfathomable epoch, due to the accelerating expansion of space, it becomes statistically probable, indeed almost certain, that within the entire observable universe, there would exist no other particles whatsoever, apart from the starship itself. Our vessel would be traversing an absolute, unyielding cosmic darkness, a void devoid of any other light or matter. At this extreme stage, the very concept of time dilation begins to lose its meaning. We discuss the relativity of time when we can meaningfully compare the clocks aboard the ship, for instance, with clocks in the place from which we departed. However, at this advanced stage of the journey, there is simply nothing left in the entire observable universe, not merely Earth, but the entirety of previously existing cosmic structures with which to compare the onboard chronometers. The starship would have become the sole isolated locus where time, as we understand it, still exists. Beyond its confines, within the desolate expanse it traverses, the very notion of time would have ceased to hold any relevance. And the generations of astronauts born aboard this cosmic vessel, they would have no one, no external civilization or even a memory of a distant origin, to voice their profound, unspoken lament that they never, in fact, signed up for such a bleak and solitary destiny. It is highly improbable that any of their venerable great-grandparents, the original adventurers who first stepped aboard this self-contained sepulchre, would have survived to witness such an, in every sense, somber conclusion. The grim reality is that our starship, however persistent its acceleration, would never be able to reach any sort of spatial edge of the universe. This is due to the fundamental, relentless truth that the distant regions of the universe are expanding away from us at velocities that exceed the speed of light. No matter how ferociously we accelerate, we would never even be able to catch up with the edge of the observable universe, let alone the entirety of the universe itself. This, of course, was not the answer I had been seeking. It left me with a sense of the insurmountable, an intimation of an ultimate, unbridgeable frontier that seemed to mock the very idea of a finite, reachable boundary. So what then is cosmology? It is most certainly not what might first spring to mind. Cosmology stands apart, fundamentally distinct from all other branches of scientific inquiry. Typically, the scientific method involves disassembling objects or phenomena. Consider, for example, the intricate mechanics of an automobile into progressively smaller constituent parts. These smaller components are then subjected to rigorous study, delving into ever more minute and specific details. However, cosmology is the singular science that endeavors to achieve precisely the opposite. It strives to reassemble all the disparate pieces of the cosmic puzzle into a single, cohesive, overarching picture. Cosmology concerns itself with the study of the universe, and by universe, we do not mean merely the gargantuan structures of stellar systems, galaxies, and superclusters, nor is it solely about the inherent properties of space and time. Crucially, cosmology also encompasses the human being, with their profound inner capacity to understand, to interpret, and to perceive this very universe. Every individual, whether they are migrating to an unfamiliar country, participating in a revolutionary upheaval, engaging in warfare, seeking political influence, amassing or losing a fortune, entering into a sacred marital bond, or indeed undertaking any other significant human endeavor, is, whether consciously aware of it or not, profoundly influenced by their underlying convictions and beliefs about the universe. And this remains true, irrespective of whether we explicitly acknowledge it or not. What we implicitly believe, what constitutes our foundational worldview, often does not register in our minds as a belief in the conventional sense. Instead, we simply perceive it as an unvarnished truth, that the world is simply this way. The expansive history of cosmology serves as a powerful testament to this human tendency. In every epoch, within every distinct society, people have firmly believed that they had at long last uncovered the veritable, true nature of the universe. Yet, each successive era, each generation, has invariably found itself merely crafting another sophisticated mask, a conceptual framework that temporarily fit the enigmatic face of an ultimately unfathomable cosmos. The profound question then arises, will we ever genuinely ascertain the true nature of the universe? Or are we perpetually destined to merely believe that we know, only to have our models superseded by new discoveries, new perspectives? If the universe, in its deepest essence, is not what it appears to be through our current scientific lens, then how can we even begin to search for its edge? What, precisely, is it that we are truly seeking? Consider this. In the 12th century, the universe, as conceived by the German abbess Hildegard of Bingen, was depicted in a schema that, to our modern sensibilities, appears strikingly quaint. Since that distant era, we have undeniably advanced considerably in our understanding, developing far more intricate and empirically supported models. But will the people of 1,000 years hence gaze upon our current, most sophisticated cosmological model with the same sense of historical distance, the same slightly amused detachment with which we now regard the mystical, geocentric model of a 12th century visionary? It is a humbling thought, a profound invitation to intellectual humility. You might, at this juncture, interject and inquire, but why do you assume that the universe, whatever its ultimate nature, possesses an edge at all? Perhaps it is, in fact, infinite. This argument, you will find, is a venerable one, tracing its lineage back to antiquity. It is a logical proposition famously put forth by the Greek philosopher Archytas, and it was posited as proof that the universe must necessarily be infinite. Archytas's famous paradox goes something like this. Imagine an individual standing at what they perceive to be the outermost boundary of the universe. What would then transpire if they were to throw a spear beyond this supposed external limit? Would the spear recoil, deflected by an unseen barrier? Or would it pass cleanly through, sailing into an expanse beyond this world? If the spear were to pass through, it would logically imply that something, some other realm or space, exists beyond that boundary. If, on the other hand, it were to recoil, it would signify that the spear had encountered some form of limiting barrier. But then, the very existence of that barrier would itself necessitate something to limit it, and whatever limits that barrier would, in turn, require something else to limit it. This chain of reasoning, Archytas argued, extends infinitely. Therefore, the universe, by this logical deduction, must be infinite. For over 2 millennia, the most brilliant minds have grappled with this profound enigma, and it is safe to assert that Archytas's paradox has significantly shaped, and indeed often constrained, the historical development of cosmological thought. However, what the ancients, with all their intellectual prowess, did not grasp was a profound counterintuitive truth. The universe can, in fact, be infinite, and yet simultaneously possess neither an edge nor a boundary in the conventional sense. It is common knowledge that the sum of the angles within any triangle amounts to 180 degrees. However, this seemingly inviolable geometric truth is, in fact, not entirely accurate in all contexts. As far back as the 19th century, one of the most towering figures in the history of mathematics, Carl Friedrich Gauss, began to harbor suspicions about this very axiom. To understand his insight, let us engage in another thought experiment. Imagine that we are not three-dimensional beings, but rather two-dimensional creatures, dwelling on the surface of a spherical planet. In such a scenario, the surface of our planet would effectively constitute our entire cosmos. If, within this two-dimensional world, we were to inscribe a small triangle on the surface of our planet and measure the sum of its internal angles using our standard two-dimensional instruments, we would indeed obtain the familiar sum of 180 degrees. However, if we were to meticulously construct a triangle of truly immense proportions, spanning vast distances across our spherical world, even with crude instruments, we would invariably discover that the sum of its angles would be greater than 180 degrees. Gauss, with his unparalleled mathematical intuition, hypothesized that our own three-dimensional space might similarly possess an inherent curvature. In such a curved three-dimensional space, he reasoned, the sum of the angles of a sufficiently large triangle would necessarily deviate noticeably from the Euclidean ideal of 180 degrees. As far as we know, Gauss, working in secrecy, utilized sophisticated geodetic instruments to measure a colossal triangle formed by the peaks of 3 mountains in Germany. He did indeed observe a slight deviation in the sum of its angles from 180 degrees, but this variation fell within the accepted margins of experimental error, rendering the results inconclusive by the standards of his time. The reason for his secrecy was practical. Imagine the reaction of his academic contemporaries. A man of his stature, attempting in all seriousness to detect a deviation in the sum of a triangle's angles, would have been perceived as pursuing an absurdity, akin to someone meticulously trying to find an error in the sum of 2 plus 2. Even given Gauss's immense reputation, the most charitable interpretation would have been that he had simply lost his intellectual bearings. Similarly, the brilliant mathematician Nikolai Lobachevsky, despite his profound contributions, faced severe professional ostracization and ridicule for his pioneering work on non-Euclidean geometry. Ultimately, it was Albert Einstein's general theory of relativity, which fundamentally contradicted Euclidean geometry in its description of space-time, that was rigorously validated by experiments far more precise than those conducted by the venerable Gauss. These experiments revealed a startling truth. In the vicinity of massive objects like Earth, the angles of a large triangle, if measured with sufficient precision, could indeed sum to approximately 180.0002 degrees. This minute, yet significant, deviation from Euclidean geometry must now be accounted for in applications such as satellite navigation systems. In more extreme environments, such as the regions immediately surrounding black holes, the discrepancies between Euclidean geometry and Einstein's curved geometry become so pronounced that no special instruments are required. The distortions are visible to the unaided perceptive capacity, manifesting as seemingly impossible curvatures of light paths and apparent distortions of shape. The point I am building to is this: the universe, on its grandest scales, could theoretically curve back upon itself, much like the surface of a sphere. However, armed with increasingly precise observational technologies, scientists have meticulously measured the curvature of the cosmos across immense distances. What they have consistently found is no discernible overall curvature. While space is indeed locally curved near massive objects, when measured on the largest scales, the universe appears to be flat within the margins of measurement error. This empirical finding, if accurate, lends strong support to the notion of an infinite universe. The theoretical physicist Max Tegmark, in his compelling work, Our Mathematical Universe, posits that the total number of all possible unique combinations of particles within our observable universe amounts to a staggering figure, approximately 10 to the power of 10 to the power of 118. This is a number of truly colossal, almost unimaginable magnitude. But if the universe is, in fact, infinite, then this proposition leads to a truly mind-bending implication. It suggests that if one were to project a straight line from Earth in any given direction, then after traversing a distance equivalent to 10 to the power of 10 to the power of 118 times the diameter of the observable universe, that line would invariably intersect with an exact replica of Earth. On this distant, identical Earth, there would exist an exact duplicate of our observable universe, within which your precise copy would be engaged in the very same thoughts and actions that you are experiencing at this exact moment. While this notion might initially strike one as conceptually thrilling, the reality is that if the universe is indeed infinite, it leads to a host of truly monstrous philosophical consequences, some of which we have explored in previous contemplations. Trust me when I say that you would not, in the deepest sense, desire to inhabit an infinite universe. However, there are two crucial caveats to this line of reasoning. Firstly, the universe might indeed be a closed system, self-contained and finite, but its curvature might only manifest on truly gargantuan scales. In this scenario, our current measuring instruments, much like Gauss's in his time, might simply be insufficiently sensitive or expansive to detect such a subtle, overarching curvature. Our measurements, after all, only indicate that the universe is flat, with an accuracy of approximately 99.75%. This implies that if the universe is not, in fact, flat, then it must be at least 400 times larger than the observable universe. Such a scale would render its curvature imperceptible to our current methods. And secondly, the universe does not necessarily need to be curved in order to be a closed, finite system. Consider, for example, the surface of a cylinder. Geometrically, it is considered flat because parallel lines drawn upon its surface will remain parallel indefinitely. This is one of the fundamental definitions of flatness in geometry. Yet, despite its flatness, it possesses a finite, closed dimension in one direction. The same principle could potentially apply to our universe. It could be absolutely flat, exhibiting no large-scale curvature, and yet simultaneously be a closed system. For instance, in a universe conceptualized as a four-dimensional sphere, the sum of a triangle's angles would indeed exceed 180 degrees, and parallel lines would eventually converge. However, in a universe shaped like a four-dimensional torus, none of these phenomena would occur. In such a topology, space would appear to be flat, much as our current observations suggest. Nevertheless, if you were to travel in a perfectly straight line, you would, eventually and inevitably, return to your precise point of origin. This intricate exploration reinforced my conviction that the probability of ever physically reaching an edge of the universe is vanishingly small, almost nil. But then, a new thought, an intriguing possibility, began to coalesce in my mind. Edward Harrison, in his insightful treatise, observes, "Space and time, in most universes of the past, were merely the stage upon which the cosmic drama was enacted. In the modern physical universe, however, space and time are the leading protagonists." This statement resonated deeply. If space and time are indeed so profoundly fundamental, if we conceive of space-time as the very interwoven fabric from which the universe is spun, then perhaps, to apprehend the edge of the cosmos, it would suffice to simply tear that fabric. Do you comprehend the audacious implication? We, as yet, understand almost nothing about dark energy, that enigmatic force responsible for the accelerated expansion of space. It is dark energy that holds the potential to unleash a sudden, cataclysmic apocalypse, quite literally tearing apart the very texture of reality, leaving us utterly helpless to witness the universe around us fragmenting into innumerable pieces. Currently, it is believed that dark energy is not potent enough to tear apart gravitationally bound objects, such as galaxies or star systems. Therefore, its influence is thought to be primarily confined to the vast intergalactic voids, where gravitating matter is sparse. This, on the surface, provides a measure of reassurance. However, this comfort holds true only if dark energy is not, in fact, something far more potent, far more insidious than our current models suggest. A seminal article, co-authored by physicist Robert Caldwell and his esteemed colleagues, posits a chilling scenario. The epoch during which cosmic structures, as we know them, can exist might prove to be astonishingly brief in the grand sweep of the universe's history. Dark energy, under certain conditions, could conceivably lead to a cataclysmic event that scientists term the Big Rip. How might such an apocalyptic scenario unfold? Initially, the largest and most loosely bound cosmic structures would begin to unravel. The first ominous harbinger for us would be the gradual disappearance of galaxy clusters. However, to our profound dread, due to the finite speed of light, we would only become aware of this disintegration long after it had begun. By the time these signals reached us, the effects of the Big Rip would already be manifesting in our immediate cosmic neighborhood. The galaxies that comprise the Virgo supercluster, our local cosmic grouping, would begin to recede from our Milky Way at an ever-increasing velocity. Soon after, we would observe that the stars dwelling on the outer fringes of our own galaxy were no longer maintaining their accustomed orbital paths. Instead, they would be scattering chaotically into the deepening void. Our Milky Way would commence a slow, inexorable process of evaporation, its majestic spiral arms gradually dissolving. The night sky, a canvas of countless stars for eons, would grow progressively darker, the celestial tapestry fraying into an abyssal black. Approximately 7 months prior to the ultimate Big Rip, we would become aware of a subtle yet terrifying expansion of the orbits of planets within our own solar system. Earth would begin to drift perceptibly further from the Sun, and our Moon would slowly recede from Earth. Our planet, once a vibrant hub of life, would inexorably plunge into a profound, suffocating darkness and an overwhelming sense of cosmic solitude. By this stage, any cosmic structure that had, by some miracle, remained intact would be subjected to an increasingly intense stretching by the very expansion of space within its own confines. The upper layers of Earth's atmosphere would begin to boil away into the vacuum. The tectonic plates of the lithosphere, responding to the escalating chaotic shifts in local gravitational forces, would be thrust into a tumultuous, unpredictable motion. Just 1 hour before the final cataclysm, the internal pressures exerted by the expanding space would become unbearable, causing our planet to violently explode. Yet, even in this dire scenario, a few intrepid individuals might, theoretically, survive this initial cosmic dissolution. Those who, with remarkable foresight, had managed to discern the nascent signs of the impending cosmic demise and had fled Earth aboard a specially designed rocket. The smaller the astronaut's capsule, the better, for when the threat originates from the very fabric of space itself, it is advantageous to occupy as little of that space as possible within one's protective vessel. However, this reprieve would be agonizingly brief. Soon, the electromagnetic forces, those fundamental bonds that meticulously hold together the atoms and molecules constituting the human body, would no longer be able to resist the relentless internal expansion of space. The very molecules of their being would begin to dissociate, to fragment, and all the inhabitants of the cosmic capsule would be torn apart from within. They would perish, never quite witnessing the ultimate moment for which we have gathered here tonight. In the final horrifying moments, roughly 10 to 20 seconds before the Big Rip itself, the atoms composing all matter would disintegrate. And then, at last, The very fabric of space-time would be rent asunder. No point, I mused, reflecting on this gruesome scenario. Firstly, humanity, by all logical projections, would certainly perish long before ever actually perceiving the tearing of space-time. And secondly, while the precise figures vary depending on the specific model, this catastrophic event, if it is to occur at all, is not predicted to happen for several tens of billions of years. Whether humanity, as a species, will even endure until such a distant epoch remains a formidable question. And what truly does the tearing of the fabric of space-time even signify? It remains a concept profoundly difficult to grasp, leaving me still searching for a more tangible, more immediate edge. But since space is expanding, does it not necessarily expand into something, perhaps into a higher dimensional space? If this were the case, then what if the boundary of our universe passes directly through us, right under our very noses, and we simply remain oblivious to its presence? What if our universe is but a part of something grander, a component within a realm of higher dimensions? If these conjectures hold any truth, then perhaps we could, at the very least, catch a fleeting glimpse of that higher realm, or even, perhaps momentarily extend a hand into it. And indeed, the leading candidate for a theory of everything, specifically M-theory, offers precisely such a framework. It posits that our universe is, in essence, a brain, a membrane, possessing 3 spatial dimensions and 1 temporal dimension, existing within a larger hyperspace. This hyperspace, M-theory suggests, contains an additional 6 spatial dimensions, curled up or compacted in ways we cannot perceive. It sounds, I admit, like something conjured from the realm of science fiction. Yet, even the most respected and rigorous physicists take this theory with the utmost seriousness, devoting immense intellectual effort to its development and refinement. According to M-theory, all these additional, hidden dimensions are, in fact, omnipresent, existing right here, all around us. So what then prevents us from simply stepping into them? Unfortunately, the very laws of physics, as we currently understand them, pose the primary obstacle. The atoms and subatomic particles that constitute our bodies, the electromagnetic fields that mediate all light and chemical interactions, the strong and weak nuclear forces that bind atomic nuclei together. All these fundamental elements of our existence appear to be inextricably confined to our familiar 3 spatial dimensions. Every attempt by brilliant physicists to formulate how known matter, fields, and forces might interact with larger extra dimensions has, quite consistently, led to the conclusion that virtually all particles, forces, and fields known to humanity are fundamentally stuck within our native 3 spatial dimensions. There is, however, a singular and profound exception: gravity, and the associated curvatures of space-time. The peculiar leakage of gravity into these other dimensions is a theoretical mechanism that helps explain why gravity, in our familiar 3 dimensions, appears to be so incredibly weak in comparison to the other fundamental forces. To illustrate this disparity, a weak refrigerator magnet can effortlessly defy the gravitational pull of an entire planet holding a piece of paper against a metallic surface. This striking example underscores gravity's relative feebleness. So while gravity can, theoretically, traverse these additional dimensions, my hand, alas, cannot. However, it remains an intriguing possibility that other, yet unknown, types of matter, fields, or forces might exist that are capable of existing within a greater number of dimensions. In such a scenario, these exotic entities could potentially penetrate into our 3-dimensional reality, interacting with us in ways we might not yet comprehend. You have undoubtedly encountered similar demonstrations countless times, but for those who haven't, allow me to clarify with an analogy. Imagine a two-dimensional universe, a flat plane, conceptually embedded within a higher dimensional space, specifically a three-dimensional space. Within this two-dimensional universe, there is a room, and inside this room a two-dimensional inhabitant has taken refuge, sealing themselves off. Another two-dimensional person on the outside would be utterly unable to enter. However, now introduce into the higher three-dimensional space an object, let's say a cylinder. For this three-dimensional cylinder, there are no impediments whatsoever to entering the two-dimensional person's room. As it passes through their flat world, the two-dimensional inhabitant would not perceive the entire cylinder. Instead, they would only observe its two-dimensional cross-section, perhaps a circle or an ellipse, depending on the angle of intersection. Now let us transpose this illustrative scenario to our own three-dimensional universe. It is entirely conceivable that, in a precisely analogous fashion, a four-dimensional object could enter my home. How would such an event manifest itself to our three-dimensional senses? The precise nature of multidimensional phenomena remains, as yet, largely beyond our direct apprehension. However, this conceptual void does not deter certain physicists from engaging in informed conjecture. For instance, there is a reasonable, albeit only partially substantiated, hypothesis that suggests if multidimensional fields, forces, and particles do indeed exist, we might never be able to directly perceive or experience them through our conventional senses. That is to say, if something from hyperspace were to pass through our three-dimensional brain, we would likely not be able to see its constituent parts. The cross-sections of such an entity might appear transparent or utterly beyond our sensory input. However, there is one peculiar phenomenon that we might indeed detect. Recall that, according to M-theory, gravity is the sole force capable of propagating across all dimensions. Therefore, if an entity from hyperspace were to possess a sufficiently strong gravitational pull, it would subtly, yet measurably, bend the rays of light passing through its localized presence. This gravitational lensing would subtly distort our perceived images of the surrounding reality, causing an almost imperceptible ripple in the visual fabric. Furthermore, if this entity were to be rotating, it could potentially entrain the very space around it in a swirling vortex-like motion. This frame-dragging effect, a prediction of general relativity, could, in principle, be felt and observed, manifesting as a strange, unearthly current in the fabric of space-time itself. Our evolutionary trajectory has been confined to a three-dimensional world, rendering four-dimensional objects inherently counterintuitive and profoundly alien to our cognitive frameworks. Yet, here is where things become truly fascinating. A remarkable study investigated the capacity of human beings to navigate a virtual four-dimensional maze. The experiment employed a specially designed game, allowing participants to interact with a simulated higher-dimensional environment. The research unequivocally demonstrated that the mechanisms of spatial processing within the human brain are not rigidly constrained to perform computations solely within a three-dimensional framework. Instead, the results indicated that, after a relatively brief period of training and adaptation, individuals were surprisingly capable of developing a reasonable proficiency in orienting themselves within a four-dimensional environment. The human brain, it seems, is a remarkably flexible and adaptable instrument. What is even more astonishing is that, according to M-theory, hyperspace might not only contain our universe, but a multitude of other universes as well. And these other universes are not necessarily confined to some impossibly distant realm. It is theorized that higher dimensions could influence our universe in various subtle ways. Though our current human technologies have not yet achieved the precision required to empirically measure these influences through physical experiments. In any case, this particular avenue of exploration, while conceptually tantalizing, ultimately presented a similar practical dead end for my quest. What utility, I pondered, are all these additional dimensions if, even hypothetically, one can only be entered from them into our own and not the other way around? The possibility of actively traversing these higher dimensions, of exploring a true outside, remained beyond our grasp. Perhaps one of the most central and profound insights that Edward Harrison endeavors to convey in his influential book is this: regardless of whether future experiments ultimately confirm M-theory or not, it will, fundamentally, remain a model. It will be yet another conceptual framework, a sophisticated lens through which we attempt to apprehend reality. It will be a model that is either capable or incapable of adequately describing specific aspects of our capital U universe. This is because, for every individual, the concept of the universe is inherently subjective, deeply personal, and often shaped by their unique worldview. For those inclined towards religious faith, the universe is a divinely crafted realm, purposefully governed by supernatural forces and imbued with sacred meaning. For artists, it is a world of exquisite sensitivity, a canvas of aesthetic beauty revealed and interpreted through the lens of human emotion and perception. For academic philosophers, it is a complex tapestry of logical, analytical, and synthetic structures, ripe for rigorous inquiry and deconstruction. And for scientists, it is a meticulously observed world, a realm of controlled experiments, its phenomena explained by the elegant and impersonal forces of nature. And for each of these perspectives, their particular model, their specific conceptualization, can be perceived as the true universe, the definitive reality. Consider, for example, the Ptolemaic model of the cosmos. Ptolemy, a towering figure in ancient astronomy, devised a geocentric model with a stationary Earth at its center. This model not only provided a remarkably accurate explanation for the observable movements of the planets, but also allowed for the calculation of their future positions with a precision that was more than sufficient for the imperfect, naked-eye observations available at the time. For over 1,000 years, people lived within a universe where the sun, moon, and stars revolved around the Earth, and this model functioned admirably, offering a coherent and largely predictive description of reality. Then, in the year 1500, a revolutionary figure emerged, Nicholas Copernicus. He presented his mathematical model of a heliocentric system, placing the sun, rather than the Earth, at the center. Interestingly, Copernicus's initial model, in its raw predictive power, actually described the movements of the planets less accurately than Ptolemy's long-established system. Today, what we refer to as the Copernican principle asserts the mediocrity of Earth's and the Sun's position, suggesting that our location is in no way special or privileged within the vastness of the universe. Yet, Copernicus himself did not simply place the Sun in a center, but in the center of the universe, which he still conceived of as finite and bounded by a solid cosmic sphere into which the fixed stars were embedded. Later, the brilliant Johannes Kepler, whose contributions to science are almost impossible to overstate, was absolutely enraptured by Copernicus's idea of a sun-centered cosmos. He meticulously refined and improved Copernicus's model, driven by a fascinating blend of scientific rigor and theological conviction. Do you know why? Kepler, in his profound theological beliefs, considered the Son to be analogous to God the Father, and thus it had to reside at the center. The sphere of fixed stars represented the Son, and the space between them, the Holy Spirit. His seminal work, Mysterium Cosmographicum, even included a substantial chapter dedicated to reconciling the central position of the Sun with various biblical passages. It is to these very astronomy books, infused with both scientific insight and spiritual conviction, that modern astronomy owes a considerable debt. Edward Harrison compellingly argues that every society in its own historical moment invariably constructs its own unique picture of the world. This collective cosmology, he suggests, is like a finely crafted mask that is meticulously placed upon the face of the unknown universe. As we have explored tonight, our contemporary era is not merely characterized by different models of a single universe, but rather by a proliferation of different universes within various cosmological models. Consider again the M-theory, where our universe is conceptualized as a brain within a higher dimensional hyperspace. This theory inherently implies the existence of other brains, each representing a distinct, separate universe. In the captivating models of eternal inflation, there are thought to be an infinite multitude of universes, each possessing its own unique set of fundamental physical parameters. In the intriguing model proposed by physicist Lee Smolin, new universes are perpetually born within the event horizons of black holes. The list of these multiversal conceptualizations extends almost infinitely. Therefore, Harrison argues, when we use the grand and imposing word universe, rendered with a capital U, it inadvertently conveys the impression that we are privy to and have definitively captured the ultimate, true nature of all existence. By designating our current, most sophisticated cosmological model as the universe, capital U, we perilously overlook the crucial, humbling truth that this model, like all its predecessors, is destined to eventually meet a similar fate. We, as humans, frequently commit the intellectual error of mistaking the mask for the face, our model of the universe, for the universe itself. Our ancestors, across countless generations, consistently made this very mistake. And our descendants, looking back from their future vantage point, will, in all likelihood, perceive us repeating this very same error. Since we are fundamentally incapable, even in our most fervent imaginative flights, of truly apprehending the ultimate intrinsic nature of the universe, we can, as Harrison suggests, humbly circumvent such presumptive claims by employing a more modest and appropriate term, universe, with a small u. This linguistic distinction serves as a potent reminder of the inherent limitations of our current understanding, acknowledging that our grandest theories are but provisional approximations of a reality that may forever elude our complete grasp. But then, one might reasonably ask, could there not eventually come a moment when we truly comprehend everything about the universe? From Harrison's perspective, the answer is a resounding no. And it is this profound assertion that gradually guides us toward the ultimate understanding of my initial question. The edge of the universe he proposes is not merely a spatial concept. It is also a temporal one. The universe, as we currently understand it, had a definitive beginning in the singularity of the Big Bang, and thus possesses a time-like edge at its genesis. If this universe were, in some distant future, to recollapse into another singularity, an event often termed the Big Crunch, it would then possess two such time-like edges, a beginning and an end. These cosmic temporal boundaries, however, are not to be imagined as solid cliffs or impenetrable walls. Rather, they are more akin to a gradual, inexorable dissolution, a fading away into the ineffable. Since time itself, much like space, is understood to be a physical dimension and an integral component of the physical universe, we can assert that physical time is contained within the physical universe and cannot, by its very nature, extend beyond its confines. Thus, in a model encompassing a Big Bang singularity and a Big Crunch singularity, time, as a measurable and coherent phenomenon, can only exist within the intermediate span between these two cataclysmic events. The very problem of the existence of cosmological singularities represents one of the most formidable challenges within physical cosmology. The crux of the issue lies in this. Absolutely none of our intricate knowledge regarding the events that transpired after the Big Bang singularity can furnish us with any meaningful information about what occurred before it. Consider a simple analogy. If a ball suddenly flies towards you, you can, with a high degree of certainty, infer what must have happened moments before. You mentally reconstruct a chronology, establishing a causal link. The ball could not have simply materialized from thin air. Therefore, it must have been in flight for a certain duration from the point of its launch. However, all such logical extrapolations and causal reasoning utterly break down when we attempt to apply them to singularities. And conversely, nothing that occurs before a Big Crunch singularity can provide any information about what will happen after it. These are, in essence, points within space-time where the fundamental laws of cause and effect are utterly violated. It is conceivable that the physical world, with its orderly sequence of events unfolding in cosmic time, simply dissolves at these initial and terminal points, transforming into a chaotic, disordered metric foam. But, in truth, our understanding of these time-like cosmic boundaries remains woefully inadequate. Perhaps this deficiency stems from our equally poor comprehension of the very nature of time itself. But then another thought occurred to me, pushing the boundaries of this contemplation. We need not necessarily await the ultimate end of time, the distant Big Crunch. The Big Bang and the Big Crunch are not the sole locations where we might potentially glimpse the boundary of space-time. In fact, we might be able to achieve this relatively nearby. As early as the groundbreaking work of Roger Penrose, it was demonstrated that when a dying star collapses under its own immense gravity, a singularity must inevitably form. This singularity represents a point, or rather a region, within space-time, where the most fundamental categories of existence, space and time themselves, approach a definitive end, ceasing to exist in their coherent, measurable forms. Thus, all that we theoretically require is a single black hole and a copy of a particular book by Kip Thorne. Kip Thorne, for those unfamiliar, is the brilliant mind behind the scientific conceptualization that lent such scientific rigor to the film Interstellar, elevating it to one of the most scientifically grounded works of modern cinematic science fiction. Beyond his involvement in that iconic film, Thorne is widely recognized as one of the world's foremost authorities on Albert Einstein's theory of relativity, and indeed, a recipient of the Nobel Prize in Physics in 2017. His book, The Science of Interstellar, provides a detailed scene-by-scene analysis of the film's scientific underpinnings. However, Thorne also penned another monumental work, Black Holes and Time Warps, Einstein's Outrageous Legacy, in which the term singularity appears a remarkable 266 times. If one were seeking accessible yet profoundly insightful information about these enigmatic cosmic entities, I reasoned, this would be the definitive source. So, strictly speaking, black holes, within which singularities reside, are not in themselves the directly lethal objects. Rather, they are regions of space where the forces are so extreme as to be fatal. Let me reiterate, a singularity is a region where, According to the laws of general relativity, the curvature of space-time becomes infinitely large, and space-time itself effectively ceases to exist. This, it seemed to me, was precisely what I had been searching for. Let us, then, finally confront this profound edge, utilizing the mask of the universe known as general relativity. Friends, at this point, I require your absolute, undivided attention. This particular segment of our journey into the cosmic unknown is intricate and demanding. But if you can navigate its complexities, you will likely gain an understanding of the deepest mechanics within black holes that few ever acquire. In my previous exploration of Interstellar, I meticulously deconstructed Kip Thorne's explanations of what transpired with the character Cooper after he crossed the event horizon of the gargantua black hole almost on a frame-by-frame basis. However, in the film, Cooper never actually entered the singularity itself, as he was retrieved by the enigmatic Tesseract just before reaching that ultimate point. Here, however, we shall delve into the harrowing events unfolding within the singularity, the very point where the space-time continuum, as we know it, finally terminates. This is, of course, based on our current understanding. I have no concept how, with my limited tools, I will attempt to convey this visually in other mediums, but here, in the theater of the mind, let us proceed. A black hole, at its fundamental core, is a region of space where gravity is so overwhelmingly powerful that the very fabric of space-time, ponder this deeply, becomes so warped and curved that it literally folds back upon itself, thereby sealing off all pathways of escape into the external universe. Imagine an astronaut, feet first, falling into a black hole. For this thought experiment, a small black hole, say a few times the mass of our Sun, would be unsuitable. Its event horizon, the point of no return, would be only about 10 to 15 kilometers in diameter. But within a mere 150 kilometers of its center, the tidal gravitational forces would intensify to such an extreme degree that they would violently rip the falling astronaut in half right down the middle of their torso. Subsequently, each half of the torso would be torn in half again, and again, in a geometric progression, until the unfortunate individual was utterly dismembered, their body reduced to elementary particles, even the atoms themselves unraveling. Thus, the astronaut would not survive long enough to even cross the event horizon, let alone reach the singularity. However, if the black hole is truly massive, the scenario becomes profoundly different. At the heart of our own galaxy, some 27,000 light-years distant, resides the supermassive black hole Sagittarius A*, boasting a mass exceeding 4 million suns. Such a colossal entity would suit our purposes perfectly. The larger the black hole, the longer an astronaut could potentially survive within its gravitational embrace, falling towards its center. In a black hole with a staggering mass of 10 billion suns, an astronaut, having crossed the event horizon, would continue to fall for several hours, experiencing no discomfort whatsoever. It would be only in the final second before reaching the singularity that they would begin to perceive a terrifying phenomenon. Their legs and head would feel as though they were being stretched immeasurably, while their torso was simultaneously compressed laterally. In the fleeting hundredths of a second preceding the singularity, these stretching and squeezing forces would become so overwhelmingly intense that the bones and soft tissues of the human body would yield, tearing the body apart and leading to the astronaut's inevitable demise. When the remnants of the astronaut's body ultimately reach the singularity, the stretching and compression of space itself become infinitely large. In accordance with the laws of general relativity, the astronaut, or what is left of them, effectively merges with the singularity, becoming an inseparable part of its infinite density. The astronaut cannot pass through the singularity and emerge on the other side because, as the same general theory of relativity dictates, a singularity possesses no other side. Space and time, as distinct entities, and indeed the very categories of space-time itself, cease their coherent existence within the singularity. If we were to conceptualize the space-time of a black hole as a sheet of paper, then the singularity would represent its razor-sharp edge, the point where the very fabric of space-time abruptly terminates. However, unlike a sheet of paper across which an ant might crawl to the edge and return, nothing that enters a singularity can ever return. Astronauts, particles, waves, everything that falls into it is, according to Einstein's theory of gravity, instantaneously annihilated in its classical form. But here lies a crucial, gargantuan caveat. Thorne meticulously explains that the aforementioned illustration, while helpful for initial understanding, does not fully clarify the mechanism of destruction, as it inherently disregards the profound curvature of space. In reality, when the astronaut's body reaches the singularity, it is not merely stretched delicately, as some simplified diagrams might suggest. Instead, it is stretched lengthwise to an infinite extent, while simultaneously being compressed laterally to a size of absolute zero. How one might envision this defies conventional human intuition. How can a body become infinitely long, yet its head not protrude beyond the event horizon? How can its head and feet be drawn into the singularity, with an infinite expanse between them, yet simultaneously the width between its left and right arms be reduced to absolute zero? This is the realm where common sense, rooted in our three-dimensional experience, utterly fails. Of course, it is not only the astronaut who experiences the exquisite horrors of approaching the singularity. According to the Oppenheimer-Snyder equations, all forms of matter, even individual atoms, and the electrons, protons, and neutrons that constitute them, even the quarks that compose protons and neutrons, are subjected to this infinite stretching and compression. This all sounds dramatically captivating, yet profoundly implausible. For while infinities are perfectly acceptable constructs within mathematics, their appearance in physical reality almost invariably signals a fundamental breakdown in our understanding. Physicists, universally, harbor deep skepticism whenever their equations yield infinities, regarding them almost always as a telltale sign of an error or an incompleteness in the underlying theoretical framework. The infinite stretching and compression within a singularity are no exception to this rule. It is here that the laws of quantum mechanics, which notoriously stand in conceptual opposition to the laws of general relativity, enter the fray. They simply do not concur with such a cataclysmic, infinite outcome. Thorne clarifies that quantum mechanics fundamentally prohibits the existence of all forms of true infinities. Extremely close to the singularity, a realm we currently understand very poorly, a momentous convergence occurs. The laws of quantum mechanics begin to merge with the laws of general relativity, completely transforming the rules of the cosmic game. These new governing principles are termed the laws of quantum gravity. Quantum gravity comes into effect when the fluctuations of the tidal gravitational forces become so immense that they utterly deform all objects. This occurs at an unfathomably brief temporal scale, approximately 10 to the power of minus 43 seconds, or even faster. Yes, the forces are unbelievably savage, but the fluctuations are still demonstrably not infinite. By this point, the astronaut is assuredly dead, their body parts thoroughly commingled, and the atoms that once comprised them are distorted beyond any recognizable form. Yet crucially, nothing is truly infinite. The game, as it were, continues. And it is precisely at this juncture, within this infinitesimally small and incredibly dense region, that quantum gravity radically alters the very nature of space-time itself. My vision is not what it once was, and so I have reread this particular passage multiple times, ensuring that my perception was not playing tricks on me. Are you ready? Quantum gravity, it is theorized, tears apart the very connection between space and time. Let me repeat that, just to ensure the profoundness of the statement truly lands. Quantum gravity severs the link between space and time. It literally pries space and time apart from one another. Subsequently, it fundamentally destroys time as a coherent concept, and it obliterates the very definiteness of space. Time simply ceases to exist. We can no longer meaningfully assert that this happened before that, because without time the concepts of before and after are rendered utterly meaningless. Space, or rather, what was once the unified entity of space-time, transmutes into a probabilistic foam, a frothing, chaotic sea of possibilities. A brief respite, and then a direct quotation from Kip Thorne, who endeavors to render these abstract concepts more comprehensible. Before the rip, meaning outside the singularity, space-time resembles a piece of wood saturated with water. In this analogy, the wood represents space and the water represents time. Both categories, wood and water, space and time, are tightly intertwined and unified. Within the singularity, however, the laws of quantum gravity that govern it are akin to fire thrown upon such a damp piece of wood. The fire in this analogy evaporates the water from the wood, and the wood is left alone and unprotected. Similarly, within the singularity, the laws of quantum gravity destroy time, and space remains alone and unprotected. Then Thorne continues, the fire transforms the wood into a foam of flakes and ash. In an analogous fashion, the laws of quantum gravity transform space into a random probabilistic foam. It is precisely this random probabilistic foam that constitutes the singularity, and this foam is governed by the elusive laws of quantum gravity. Within this foam, space possesses no singular definite form. It exhibits no fixed, predictable curvature, nor even a stable topology. Instead, there exists only a probability for this or that curvature, for this or that topology. For example, within the singularity, there might exist a 0.1% probability that the curvature and topology of space assume a particular form, a 0.4% probability that they take another form, a 0.02% probability for yet a third form, and so on. Do you comprehend the profound implication? This does not mean that space spends 0.1% of its time in the first form, 0.4% in the second, or any other such temporal distribution. Because, let me reiterate, within the singularity, there is no such concept as time. Furthermore, since time is absent, it is utterly meaningless to ask whether space assumes form B before or after it takes on form C. The only question that retains any meaning with regard to the singularity is, what is the probability that space possesses form A, B, or C? And the answers would be 0.1%, 0.4%, and 0.02% respectively. My mind reels with the sheer audacity of this concept, because this, in essence, is what the boundary of the universe looks like, at least according to the limits of my current search. It feels like at least something, a tangible, albeit utterly abstract, conclusion. I am utterly at a loss to visualize such a state of affairs. But this, precisely, is the profound utility of mathematics. It allows us to manipulate and explore concepts that lie beyond the grasp of the human imagination. And this, then, is one of the ultimate capabilities of modern cosmology. It enables us to investigate the literally unimaginable. You might at this juncture raise a valid objection. Even if this theory holds true, no astronaut falling into a black hole would ever actually perceive this boundary of space-time. You yourself stated that they would be torn to shreds beforehand. And this observation, I concede, is entirely accurate. However, there's another fascinating twist. As meticulously detailed in calculations performed in 1991 by Werner Israel and Eric Poisson from the University of Alberta, and also by Amos Ori, a postdoctoral researcher in Thorne's group at Caltech. This will sound incredibly counterintuitive. The chaotic tidal forces within a black hole actually weaken over time. Allow me to elaborate. For instance, if a colossal black hole with a mass of 10 billion suns were to be newly formed at the center of some galaxy, and an astronaut were to immediately begin falling into it, then yes, they would be violently ripped apart. But if one were to judiciously wait for several years, then by that time, the tidal forces of the singularity would have become so incredibly gentle that, astonishingly, an astronaut could not only survive them, but might even pass through them without any discernible discomfort whatsoever. The astronaut would, theoretically, reach the very edge of the probabilistic, quantum gravitational singularity almost entirely intact and unharmed. This, incidentally, is precisely what was depicted in the film Interstellar just prior to Cooper's entry into the Tesseract. And it is only at the very precipice of this singularity, when the astronaut is finally face to face with the ultimate laws of quantum gravity, that we enter a realm of profound uncertainty. We genuinely have no concept of whether they would perish or survive, because our understanding of the laws of quantum gravity and their ultimate consequences remains profoundly incomplete. You might argue, very well, I grant you that, but you have cleverly substituted the concept of the boundary of the universe with the concept of the boundary of space-time, and you are correct. It is a subtle, yet significant conceptual shift. Yet what, I ask, could be more fundamentally foundational than space-time itself? On one hand, it seems almost impossible for a finite universe to exist, beyond which there is absolutely nothing. And it is entirely plausible that our universe does indeed possess something external to it, and simultaneously, it might also be infinite. But on the other hand, the elegant simplicity of mathematics does not demand anything external to the universe. The universe is not necessarily compelled to be a kind of spherical entity, passively floating in the midst of some unknowable void. From a third, and ultimately most crucial perspective, everything, absolutely everything, hinges upon how we fundamentally define the universe itself. If, from your vantage point, the term universe signifies, quite literally, all things that can possibly exist, then by definition, there can be nothing outside the universe. For anything that we might conceive of as residing outside, whether it be formless, unknowable, or even consisting of absolute nothingness, an utter void, all such concepts are, by their very nature, still existing entities. And consequently, by definition, they are part of the universe. We cannot embark on a journey to the edge, as Dante and Beatrice did in the Divine Comedy, to gaze upon the entire universe from some celestial tribune. But what underpins Harrison's profound certainty that we will always operate solely with models of the universe, and never truly apprehend its intrinsic, ultimate nature? Well, on one hand, this certainty stems from the inherent limitations of the scientific method itself, no scientific theory can ever be definitively proven. It can only be disproven or falsified. Therefore, we can never be absolutely certain that we are not merely donning another sophisticated mask upon the enigmatic face of the unknown universe. But Harrison's primary argument delves far deeper, and I was struck by its profound resonance with concepts I explored in a previous contemplation concerning the nature of consciousness. That particular video was, incidentally, inspired by the writings of another brilliant physicist, the esteemed Erwin Schrödinger, so perhaps this resonance is not entirely surprising. The essence of Harrison's argument is this: modern scientific cosmology rigorously investigates a universe that explicitly includes all that is physical and explicitly excludes all that is non-physical. What constitutes the physical? It encompasses everything that is amenable to measurement, everything that is connected to concepts that, at least in theory, can be subjected to empirical falsification. Atoms and galaxies, cells and stars, organisms and planets, these are all physical entities belonging unequivocally to the physical world. But there is something else, something profoundly distinct. We, as physical beings, possessing bodies and brains, are undeniably contained within this very physical universe, a universe that is amenable to measurement and scientific inquiry. And yes, the physical universe has been astonishingly successful in explaining the intricate workings of various phenomena, allowing us to exercise remarkable control over our surrounding environment. However, it is fundamentally incapable of explaining mental or psychic phenomena, such as consciousness and self-awareness. These subjective experiences are not directly amenable to measurement within the current scientific paradigm. An individual who persistently inquires, where precisely is the mind located within the physical world, would find themselves traversing a circuitous path through various scientific disciplines in their search for an answer. Biologists might assert that life and mind are emergent manifestations of incredibly complex physical systems involving billions of intricately organized cells, each cell, in turn, representing a complex organization of billions of atoms. If this explanation fails to satisfy, the biologists might then, with a shrug, direct the inquirer to psychologists. But alas, there exist no two psychologists who would furnish an identical, definitive answer to this profound question. Some, acknowledging the inherent limitations of their field, might then direct the inquirer to physicists, reasoning that physicists are the ones who grapple with the truly fundamental aspects of reality. Yet physicists, in turn, might either outright deny the existence of the problem, arguing that for many physicists, that which cannot be measured simply does not exist. Or they might politely recommend a return visit to the biologists, asserting that such questions fall outside the purview of their specific domain. In a state of intellectual desperation, the inquirer might then contemplate seeking the counsel of cosmologists. For if other scientists can endlessly deflect this profound enigma by declaring it beyond their area of expertise, cosmologists, by the very nature of their discipline, study the entire universe, and the enigma of consciousness stares them directly in the face. What, then, would a specialist in this grand field, what would Edward Harrison himself respond? Consider this evocative painting by M.C. Escher, Moritz Cornelis Escher, the beloved artist of physicists and mathematicians alike. It is a self-portrait, to be precise. In this artwork, the artist depicts himself within a reflective sphere, holding the very sphere in which he is reflected, and within that reflection, one can discern the artist again, holding the sphere and so on, in an infinite regression. This, it seems to me, is a powerful demonstration, an excellent visual aid for contemplating the concept of infinite regress. An argument of infinite regress is a potent challenge directed against any theory that inadvertently leads to this endless, self-referential loop. Allow me to illustrate with a simple example. The assertion that everything has a cause leads directly to an infinite regress because one can then endlessly inquire, and what was the cause of that cause? And then, what was the cause of that cause? Ad infinitum. Thus, if we acknowledge the logical force of the argument from infinite regress, we are compelled to concede that the statement, everything has a cause, is ultimately absurd and therefore false. Cosmology, Harrison argues, is fundamentally incomplete in a profound sense because we consistently fail to adequately place ourselves, the cosmologists, within our own models of the universe. The universe, in its entirety, possesses self-awareness, for it demonstrably contains us, as intelligent, self-aware beings. Yet the physical universe, as described by our scientific models, possesses no self-awareness, and it does not explicitly contain us as beings endowed with consciousness. We can assign our bodies and brains to the physical universe, which is but a model of the universe, but we cannot, without falling into an infinite loop, assign our consciousness, whatever its ultimate nature, to a universe that is comprehensible by our consciousness and subject to its study. If we attempt to do so, we enter an endless cycle. Cosmologists study the universe. There are cosmologists who study their universe, which in turn contains cosmologists, and so on, ad infinitum. It is for this same reason that artists do not typically depict themselves within the landscapes they paint. To do so would necessitate painting a picture that contained themselves, painting a picture that contained themselves, and so forth. Where, within the universe, is the rightful place for the cosmologist who is engaged in the very act of studying that universe? To resolve this profound enigma, it becomes imperative to comprehend the critical distinction between the ultimately incomprehensible universe, of which we are undeniably a part, and our comprehensible universes, with a small u, of which we are demonstrably not a part, and which we meticulously construct to explain and organize our experiences. Harrison poignantly states that it is particularly noteworthy that no physical experiment whatsoever can definitively determine whether an object possesses consciousness. If an object is before me, and I am the experimenter, I know with certainty that I possess consciousness. But by no physical instrument can I empirically prove that you possess consciousness. Consciousness is not, it seems, a property that is measurable or observable within the physical world, and it cannot, by its very nature, be explained as a purely physical phenomenon. Some scientists, grappling with this profound conundrum, postulate that consciousness simply does not exist, or at best, it is a kind of metaphysical illusion. For my part, I am not yet prepared to fully concur with such assertions. More time, more contemplation is required. It is, undeniably, rich intellectual fodder for future musings. But you know with what I absolutely, unequivocally agree even now, in this very moment. Almost certainly, the universes of the future, the conceptual models that future generations will construct, will differ significantly from our current vision. However, all of them, without exception, will remain anthropomorphic. In other words, as the ancient Greek philosopher Protagoras famously asserted, man is the measure of all things. How human beings think, how they conceptualize, how they perceive, ultimately determines how they understand their own universe. Of course, the universe itself was not created by humanity. But we possess no truly verifiable, unvarnished concept of what it actually is. All that we truly know is that it contains us, the very creators of these myriad universes, with a small u. Modern cosmology deals exclusively with a physical model of the universe. This, Harrison reminds us, is yet another mask draped upon the face of the unknown. But what a truly magnificent, awe-inspiring mask it is. In its intricate crafting, the entire inventive genius of the greatest thinkers in the history of science has been poured. Is it any wonder, then, that many individuals, including brilliant scientists themselves, when confronted with the sheer majesty and explanatory power of the physical universe, erroneously mistake this newest, most sophisticated mask for the genuine face, and the physical universe for the universe itself? Edward Harrison's words resonate deeply. If, after all this, you still harbor skepticism towards such profound assertions, if the anomalies that I meticulously outlined at the beginning of our contemplation have not yet swayed your perspective, then what will you make of the following revelation? Presently, the theoretical physicist Nima Arkani Hamed is actively developing a revolutionary method for calculating the interactions between particles. This approach is entirely novel, predicated upon abstract mathematics, and crucially, it does not take into account the concepts of space or time. Already, concrete examples of specific physical systems, remarkably similar to those we observe in the actual world, are beginning to emerge, systems that can be described without any reference to space-time or even quantum mechanics. Arkani Hamed's work suggests a deeper, more fundamental reality. One might be tempted to dismiss this, to say, well, this is just one individual, however brilliant, who has dedicated many years to theoretical physics and has arrived at a particular conclusion that space-time isn't fundamental. But this is not an isolated thought. Clifford Johnson, a distinguished professor in the Department of Physics and Astronomy at the University of Southern California, echoes a similar sentiment. I think we're all coming to a better understanding of one of the ideas from string theory, which is that space-time is not fundamental. Sean Carroll, a cosmologist at the California Institute of Technology whose work focuses on the foundations of quantum mechanics, is equally quick to voice his agreement on this profound shift in perspective. Space-time is real, but it's not fundamental. Just as wet is real, but not fundamental. It's just a higher-level emergent description. That doesn't mean something isn't real. The implications are staggering. The discussion, it seems, is not about whether space-time exists. It undoubtedly does in our everyday experience. However, if we were to truly comprehend its ultimate constituent nature, then at a more profound, underlying level, it would manifest as something entirely, unimaginably different. And so, tell me, in such an elusive and shifting landscape of understanding, how can one possibly seek the edge of the universe, if even that which appears to be so utterly fundamental, space and time themselves, might ultimately prove to be but another sophisticated mask, another emergent property of a deeper, more enigmatic reality? Are you still here? Given the inherent complexity and profundity of the material we have explored tonight, I truly take my hat off to you. Perhaps, of course, it is only to me that these concepts seem so intricate and challenging. But in any case, thank you for embarking on this intellectual journey with me. As the cosmic hum gently fades, and the echoes of these grand questions begin to recede, may you find comfort and peace in the quiet vastness of your own thoughts, drifting now towards the deep, rejuvenating embrace of sleep.